You can see an overview of the CPU data part in this figure. This is the instruction memory that all the instruction will be held here, and we have another memory for storing that data. We have a specific register program container which specified the address of the next instruction that should be read from the memory and will fetch from the memory and should be decoded by the remaining part of the data path. This is a logistical fight. This is the aisle view. So we have different type of instructions in the program, or type instructions, which involves the three registers. I type in instructions, which includes 2 registers and 1 data. So this ILU also computes on 2 registers when we have our type instruction, and also when we have a I type instruction, the IQ will compute 1 register and the immediate data that we have on the instruction. As you can see, we have a write part in the register file which can be used to store data in a specific register. This data can come from the memory, or it can come from the ILO. It's from this part when we have our typing instructions. The result will be completed by the ILO and it will be saved by this part in a specific register. And when we have a AI type instruction, the value will be read from the memory and it will be stored in the register. And also here, as you can see, the Atlas bus of the data memory is connected to the output of the value, the data that we want to write on the memory provided by a register from the register file. And here, let's check the data pad for instruction, fish, and program counter increment. We need 3 elements to fetch an instruction from the program memory and increment the program counter. The first one is instruction memory, a register, and a 32-bit other. This is the data part that connect these 3 elements. As you can see, the program counter is connected to the root address of the program memory. And by this way, we will read the instruction from the memory. Also, the content of the program counter is given to the other, and another input of the other is connected to the number 4. So every time for you it will be add to the program content and the result will be come back and stored in the program counter. Let me show you in a simple animation. Program counter given to the tourist part of their memory, and as you can see in the database of the memory, you can see the opcode of the instruction. Also, the program counter is given to the other and the result is coming back and stored in the program counter. So program counter is initialized or reassigned with the program counter plus 4. By this way, we will move to the next instruction in the memory. Let's check the data path or typing instructions. For these type of instructions, we need 2 elements, the register 5 and the L. This is the register 5. As you can see, you can access the content of 2 registers simultaneously by giving the index of the register 1 to this part and 5 bits for register 2 to this input. Then the content of that 2 registers will be available in the data 1 with data 2. And you can give it to the other part of the data part. Also, you can specify the write register by these 5 bits. Write register and the data that you are going to store in a register should be given to the write data part. There is a control signal register. Write that should be active when you want to write something inside the register file. And this is the new component. As you can see, it has 2 input and 1 output. There are a new control which has 3 bits. And let's check how these 2 elements can be. Construct a data pad for our typing instruction. As you can see, the instruction machine code is given to the register file. Some part of the instruction will be given to the register 1. Some part will be given to the register 2, and some part is connected to the write register. Then 2 data will be read from the registers that are inside the register file, and it will be given to the ALU. Or you perform the different operations over them according to the operations control signal. And the result will be come back and rewrite inside the one of the registers that is specified by this field. Let's check it with more detail. So as you can see, this is the 32-bit machine code instruction, and the R, S and ART fields are connected to the register number 1 and register number 2. And they are the part is connected to the write register part. So R and 1 R and 2 registers will be read. So as you can see, the register index or S and the register, which is indexed by RT field, will be read and giving to the value. Let me show you in a simple animation. All these fields are giving to the register file, and 32-bit data will be read from the register 5. And even today now you perform some operation, and the result is to back the register, which is determined by the write register. This 5 bits. Let me show you this operation in another slide. So we read or fetch one instruction from the instruction memory, and it is a 32-bit, then 5-bit. Part of our suite will be giving to the RA register, 5 bits given to the RB, and the destination field is given to the RW. Then to 32 bits data will be read from the 2 registers and giving to the L2 and L. You perform the operation on them, and the result will be come back and distort in the register that is determined by R the. So the result is connected to the bus W. Right, boss. So there are 2 control signals. A new control, which is coming from the function field. As you remember, for all of the instructions in the R type, the opcode is 0, and the function part will determine the type of the actual mathematical or logical operations that should be performed on the data. So this function part, it, a specific combination of circuit-determined IQ control and another control signal is registered, write, which is enable the register file to write the data into the register that is determined by the RB field. Let's check the data for load and store instructions. For these 2 instructions, we need 2 additional elements: a data memory unit and design extension unit. Hold data memory has oddly sparse. So by this part you can determine the address of the memory that you are going to read its content, and the content of that memory location will be available in the read data part. And also, if you want to write data, that data should be given via this write database. There are 2 control signal memory, write. That should be enabled whenever you want to write data. For example, a stored and memory read should be activated whenever you want to read the data from the data, memory modules, and the sign extension, which receives a 16-bit data and return a 32-bit data, and perform the sign extension over this input. Let's check the data pad for the load and store. As you can see, the 16-bit offset is giving to the sign extension and its commit changed to the 32 bits, and this 32 bits is given to the blue and it will be add with the base register content, which is read from the register 5. And these two data together determine the address of the memory. So the order of the memory is here, and we can read the data from the memory or we can write the data into the memory. So this is a complex data path for both of them. Let's check them one by one. So this is the data patch for load vault. As you can see in the load syntax, we have opcode to fields or SRT, or as is the base register, or DT is the destination, and we have 16-bit offset here. So as you can see, RSE and RD are giving to the register file. So we read one data from the register file and RT is given to the write register. So the destination is RD. The data will be stored in the register, indexed by artificial. So we don't use this part of the data part for this instruction. And also the immediate data will be given to the extender and sign extension is performed over them. And it's changed to the 32 bits. Now this 32 bits is given to the ILO, the content of the register, or as is also coming from this part. In this part and IL you perform addition. So the operation should be always addition. Now we have a authoress, and this atlas is given to the memory measure and one location is activated for reading. So memory, write should be 0, memory should be 1. And the content of that memory will be read and given to the write data of the register file. Now let's check the data for the store bought. For the store bought, as you can see, or is filled and filled are given to the register file. So we are going to explore the content of the register or RT inside the memory that is determined by the base register plus offset. So as you can see, again, the offset part is extended into the 32 bits. The content of the register that we are going to write in the memory is given to the write database of the memory is part. And the authoress is determined by the adding of the offset plus base register. This is the address that is computed by adding the content of the register or T plus the sign extension of the offset. So memory write control should be 1 memory. It should be 0. Operation is addition. And we don't want to write inside the register file. So register write should be 0.